Hi, I'm Sidharth Menon, one of the members of the two-member team working on the manipulating images with autoencoders. In this work, we are trying to explore the two major architectures of autoencoder, the regular autoencoder and the variational autoencoder, and we are trying to look into the applications of both of these architectures into image denoising and image inpainting using the MNIST dataset. In a way, we are trying to explore the applications of these two different architectures and trying to find the right architecture for a particular application, like the image denoising or the image inpainting. So to start with, a regular autoencoder is the one on your left, is an autoencoder that may be fully connected or it may be connected via convolutional layers. And we have two basic architectures, two basic constituents of this architecture, that is the encoder and the decoder. So you feed in an input signal, which can be an image or any other input data for that matters, can be fed into the autoencoder, and the autoencoder tries to project it into a low-dimensional latent space. And this is then fed back into a decoder that tries to reconstruct the input data. And this output of the autoencoder is actually compared with the input that was fed into the autoencoder through a loss function like the mean squared error in the case of a regular autoencoder. And in the variational autoencoder, instead of projecting your input into a low dimensional representation, which is mostly consisting of hidden units, hidden nonlinear activation units, as in the case of a regular autoencoder. In the variational autoencoder, you try to project it into a distribution, and in this case, a Gaussian distribution with a mean mu and a standard deviation sigma. And this learned sampling distribution, which represents your latent space in the variational autoencoder, tries to generate back the reconstructed input, which is nothing but the output of your variational autoencoder, and this reconstructed output is actually compared with the input to the variational autoencoder via a loss function that constitutes the mean squared error and a KL divergence function. So we try to explore mainly two major applications: the denoising, which is basically removing the noisy part of an input image, or image inpainting, which is nothing but filling up of an image consisting of missing patches. And we try to explore these two applications using the MNIST dataset, and we entirely rely on PyTorch for the implementation of these two architectures. So to start with, we first used a standard dataset like an MNIST dataset, which is a perfectly clean dataset, and we try to use these as input individual numbers from the MNIST dataset, like a 7 or a 2 or a 1, like, and so on. Like, so you try to just use these as an input to your autoencoder and try to see how good your autoencoder can reconstruct this input that is fed into them. So we try to make a comparison just to see uh, how efficient is each of them in terms of the reconstruction. And that is what we're doing here in the first section. So here we do some sort of reconstruction of this input data set, and you could see that these two are the outputs, which is nothing but the reconstructed MNIST images. That is basically done by the regular autoencoder and the convolutional autoencoder. The convolutional autoencoder is nothing but a regular autoencoder, and the only difference being that instead of a fully connected layer, you have convolutional layers, and this makes the computation a little more faster and efficient than a fully connected layer, which has a lot more parameters than the convolutional case. And one of the interesting finding here was that although by looking at looking both of these images, taking a glance at them, you cannot find that much of a difference between the ground truth data. But nevertheless, if you look closely into the convolutional autoencoder, you do really find some fine-tuned refinement of the features of these numbers and making it much more closer to the ground truth than the fully connected or the regular autoencoder. So basically, you can say one thing, that the convolutional autoencoder, it really does a pretty good job in terms of reconstruction by making it look much more closer to the actual input than the regular autoencoder. The first application now to deal with is the denoising the noisy MNIST. So for this purpose, we try to explicitly add Gaussian noises at random locations of your MNIST input data. And as you can see here, these are two sections. So basically the first four that you see belongs to one section. The next four is the second section. So basically you start with some number like a 7, and you add you add Gaussian input noise signal, and you see that it's some sort of a noised disrupted image that you have as an input. And using the autoencoder that you have trained with the clean MNIST data, you try to predict, or you try to rather make a reconstruction of this noisy input using your autoencoder. And as you can see, that the regular and the convolutional autoencoder, they really do uh, uh, put up a good performance in terms of reconstruction by removing the surrounding noises and figuring out the number that is hidden in the noisy background. So you can say that or both of them are doing pretty good job. So although you still have some noises even after reconstruction, nevertheless, it tries to obtain a clear idea of what is the image that is hidden in these noisy input data. But nevertheless, when you go into numbers like 4 in this case, 4 here is more or less, it can be considered even as a 9 in a way because of the way in which it is written. So in such kind of cases, the regular autoencoder tries to make a reconstruction that looks like an intermediate between a 4 and a 9. Rather than predicting a 4, which is a ground truth as you can see here, it tries to assume the reconstruction to be something that is closer to a 4, and it's a little more closer to a 9 as well. So it tries to, it's more or less, you can say it's kind of confused, because given the noise and given the background data, it tries to nevertheless make a pretty good prediction, I would say. And as you move into other numbers like a 5 in this case, and that you can see the 5 is more or less, it's closer, like it looks pretty much closer to a 6, and that 6 is what the regular autoencoder tries to predict. But nevertheless, you can see it also looks a kind of 5 in a way, because the ground truth, it tries to give you a prediction of more or less a number that is closer to 6 and a 5. So that's something that is an intermediate. Whereas in the last case, if you see the 9 is more or less like a perfect prediction, because the ground truth also, it also suggests that it's more or less like a 9 rather than a 4, which you might find in the first row of this layer. So um, nevertheless, you can say that it tries to make a pretty good prediction in terms of a reconstruction. Or finally, the takeaway from this section would be that it tries to obtain some sort of a reconstruction that is more or less closer to our expectations. So in denoising the noisy nest image, both the regular and the convolutional autoencoder, they really do a pretty good job. And in the image and painting of the patchy MNIST images, as you could see here, uh, the patchy MNIST, as we call it, is nothing but an MNIST that is actually explicitly you're actually removing a section of your MNIST input data so that there is a missing patch inside of an image. So basically, when you feed this as an input to the autoencoder, the expectation is that the autoencoder tries to predict the missing patched section of the image and try to make a sensible reconstruction out of this patchy input data. And so that was the expectation that we, although that was the expectation that we had for both the regular and the convolutional autoencoder, you could see here that the regular autoencoder indeed performs a pretty good prediction, pretty good reconstruction in terms of filling up these patches and trying to make a sensible prediction out of these. Whereas the convolutional autoencoder, it fails miserably in terms of its reconstruction. As you can see here in the first image, that the 7 although it was expected to give a full complete 7 as a reconstructed output. The convolutional autoencoder actually fails to uh, perform that sort of a reconstruction, whereas a regular autoencoder, although it is a kind of noisy reconstruction, nevertheless predicts uh, a shape that looks closer to the ground truth. And same applies to other numbers in the list. So if you take a 2, it really does a pretty good job, except for this noise that you have around that patchy zone. But nevertheless, you can still say that it looks closer to a 2, and the same applies to 1 or a 0, even a 4. And the 9 is kind of blurred or noisy, but still it tries to make some sort of a sensible prediction. And the same applies to the 6 and the 9 that you have, sorry, the 5 and the 9 that you have at the end. So in a way, you can say that regular autoencoder, it performs quite well in terms of the image and painting tasks, but the only issue being that the reconstruction by the regular autoencoder has an embedded noise in it, but it still tries to make some sort of a sensible prediction, whereas the convolutional autoencoder, it fails in the entire process of image and painting, maybe owing to the architecture of the convolutional autoencoder. And so the major takeaway that we can have from this sort of a image and painting task is that the regular autoencoder, it does perform quite well when you compare it to the convolutional autoencoder. And now, to go further, we also try to explore the ways in which we can try to make our architecture a little more promising in terms of performance. And one of the performance factors which we believe would be the rate of convergence or the training time taken by the autoencoder during the process of training. And so here it's basically an exploration of batch normalization and its effect on the training that we are trying to explore in this section of our work. So basically, we try to explore different architectures, the fully connected and the convolutional layer architectures, with and without batch normalization. And we come to the conclusion that the batch normalization, it really does make a drastic improvement in terms of attaining a faster convergence rate, as well as attaining a convergence in the least time when you compare it to an architecture where you don't have batch normalization. So here the orange line that you have is basically a fully connected or a regular autoencoder network without batch normalization between the layers. And as you can see that it takes quite a lot of time, quite a lot of iterations before it could finally converge to a value that is closer to what the blue, which is a fully connected with batch normalization, attains in 30% lesser time than the orange one. So essentially, the major thing that you can take away from this would be that batch normalization, it does really perform quite well in terms of reconstruction, as well as it tries to improve your training process in terms of attaining a faster convergence and in a least time. So that is one of the architectural changes that we have added. So essentially, we have tried to add the batch normalization between the layers, given all these advantages that it gives, gives your final training outcome. So finally, we also explore, and because we know that in painting, image in painting, which is nothing but the patch filling of the patchy MNIST data, we could see that the regular autoencoder, it does really perform quite well, in terms of reconstruction. There is quite a lot of noise around that patchy zone, which we want to avoid. So we try to explore the second architecture of the autoencoder, which is the variational autoencoder, and we expect that the variational autoencoder will be successful in producing much more of a continuous output, uh, because we are trying to uh, basically project your input into a sampling distribution, rather than projecting it into a hard-coded activation units in the case of a regular or a fully connected autoencoder. So that is our expectation, that the variation autoencoder really performs quite well in terms of producing continuous inputs. So we try to do some sort of an experiment with the variation autoencoder and compare it to the results for the image in painting task, and compare it with the results from convolutional and the regular autoencoder. So as you can see here that you have a uh, so you have the same set of inputs that we had used previously for regular and the convolutional cases, but nevertheless in the variational case, as you can see that the output, it does not really quite well align with your ground truth. So in the first case, as you can see, the 7, although you expect a 7 as an output, the regular indeed it does really perform well in terms of producing a 7, but with a little bit of noise, whereas the variational output is more or less, it looks closer to a 9. But nevertheless, I would just call this as a pretty much of a sensible output, because given this patch and given the surrounding input in your noise uh, in your input image, uh, you have you have actually quite a lot of possibilities in which you can actually you can actually fill this patch with many different possibilities. And so the variational autoencoder, what it tries to do is, given the surrounding information and given the patch that it has to fill, it tries to find the best set of possible outputs, uh, uh, more or less in a continuous form. So that is what you see here, that although it's a little bit blurry, it's still free of noise, and it tries to make some sort of a sensible prediction out of the given input to the to the given input that you provide it with. It tries to make some sort of a sensible prediction, and that's what you are able to see even in the all the other cases, except for the one. The one is one of those cases where you have a completely a fully reconstructed output, and it surely is a one. But in case of a zero here at the end that you see, you can see that the zero it tries to reconstruct into a six, because as you can see that if you zoom into the region of this six, it still looks like a zero. So basically, the variation autoencoder always tries to make some sort of an output that is closer or that resembles quite well with uh, the input. So although you fail in terms of producing an output that is entirely closer to the ground truth, it still tries to make some sort of a prediction that is very well in alignment with uh, the expected input data. So uh, so So the idea here is, so although you can say that the variational autoencoder fails in terms of producing an output uh, that is actually closely that resembles your ground truth data, although it fails in that fashion, nevertheless you can say that the output from a variational autoencoder is always going to be some sort of a continuous output that is not so noisy and like the regular autoencoder, but it can still produce an output that is sensible given uh, the input, whatever input that you give. So given the input, whatever input that you give, you can be sure of one thing, that it tries to predict something that is more sensible, and that is what you're seeing in this section. So if you were to ask which is the best architecture out of these, uh, one of the takeaway that you can have from here is that if you want something that is always closer to your ground truth, and that is what you are expecting, that is what you're expecting from your experiment, then regular autoencoder would be the best one to go for. And if you want to go for something that is like given a set of images, and you want to make some sort of a prediction that is closely aligning with whatever patchy input that you give, we can go for a variational architecture. So it depends on the user. So if you think about a scenario where you have a face and you remove a section of the face, like the mouth of the person, and you expect uh, the regular autoencoder and variation autoencoder to perform on that task of filling up the mouth of a person, and where the mouth of the person is actually given as blank, and that is put as an input to your encoder, and we can expect a regular autoencoder to provide you with some sort of an output that can be a lot more noisier. Whereas a variational autoencoder, on the other hand, what it tries to do would be to try to make some sort of a prediction that is more or less continuous, and that will look closely resembling to an actual phase of a person. So variational, although it does not really give you what is exactly expected from your ground truth, it nevertheless tries to give you some sort of a you know some sort of a prediction that is much more sensible, given the input that you're providing to the encoder. So, so that is something that we wish to explore in the future, because MNIST is some sort of a very limited data set that we cannot really explore beyond certain limits. So one of the tasks that we are trying to explore in the future would be to use some sort of a some sort of a three-channel, like an RGB kind of a colored image, and try to predict parts of the phases of individuals by providing the autoencoder with Apache data. So we, in that kind of a case, in that kind of a task, we expect the variational to outperform the regular or the convolutional architecture, uh, and that is something that we are yet to explore in the coming days. And now to go further, now that is to come to the final part of the first section of this work. So that is to build a generator from the trained VAE on MNIST. So basically, what we are trying to do here is we are trying to actually do variational autoencoder training. And once it has trained, we can say that the decoder of your variational autoencoder. So basically, what we're trying to do here is we are trying to train this kind of a variational autoencoder architecture, and we are trying to train it to an extent that it tries to make some sort of a sensible prediction given some sort of an input. It can be a noised input, or it can even be a patchy input. So it tries to make some sort of a sensible prediction. So we try to uh, truncate this variational autoencoder, and we try to remove this encoder part of your variational autoencoder, and tries to only use this latent space distribution along with the decoder, and we can call that more or less like a generator. And the reason why we can call this as generator, because you can feed in any sort of a random number to your mean, mu, mean, and your sigma standard deviation. You can give any sort of a random number, and still you can make sure that you get some sort of a sensible output out of this decoder. And that is the beauty of this particular area. That is, we can actually truncate your encoder out of your variation autoencoder, and you can use the rest of the variation autoencoder, and you can actually generate random images that would be sensible just by providing it with some sort of an input data. And this is more or less like something that you can closely relate to in the generative adversarial networks, wherein you have some sort of a generator that also tries to perform in some sort of a similar way. That is, given a random vector, it tries to produce an output that is much more sensible to what it has closely seen during the training time. And so even in this case with MNIST dataset, you can see that we are trying to give an input random vector representing your mean and the standard deviation, and we are able to produce an output that the generator produces, and as an outcome of its training with the MNIST dataset, it tries to produce some sort of a sensible output that, and in this case, it closely resembles an 8. And similarly, when you try different random vectors, then there are infinite combinations of such random vectors that you can provide as an input, and you're able to find quite a lot of different way and varying MNIST kind of images produced as an outcome of providing some sort of a random vector as an input. So in a way, you can call this as a generator, and this generator, just to take note of it, this generator is nothing but a generator that is a decoder, a trained decoder of your variation autoencoder, and the only difference being that you're completely chopping off the encoder part of that. And finally, what you have here is your generator, and this you can use to randomly generate MNIST output. And this is also something that we wish to explore in the future, where we try to train the variation autoencoder with different phases, image of phases, and we expect the trained decoder of that variation autoencoder to produce some sort of other phases, some different phases, which would still make sense and which would still make a lot more, continuous kind of outputs, given some sort of a random vector. So we try to explore in this direction by taking inspiration from GANs And although it's not as closely related to GANs as you can see from this, but nevertheless, we try to go in that direction in the coming future. So that is all with the first part of part of our work on manipulating images with autoencoders. And the second part is basically a lot more exploring in the direction of making uh, predictions using convolutional neural networks, which would be taken care of by Aman, who is also who's the second team member of our team, and so he'll be working closely on the rest of the area, and so I'm looking forward to that. Thank you.